Moving on to the final topic in this particular section of discussion, we have some main errors in IAR filters that we already looked into. One is related to ADC quantization noise. Then we looked into coefficient quantization error. Then we have overflow errors, which results from additions or accumulation of partial results in a limited register length. For example, if we add two 8-bit numbers, it could be resulting in an extra carry, which would result in an overflow and all those kind of things. So this is something that you already know. Then we have product round of errors. Product round of errors would be resulting from multiplying two coefficients. For example, if you multiply for two values of 4 bits each, the resultant will be 8-bit. Now if you reduce it to 4-bit, definitely value will be changing, and you can understand that from whatever we have discussed so far. Now we'll look into the last topic, that is a finite word length effect in FFT algorithms. So when we look about this particular topic, you can basically see that in FFT algorithms, which basically we have already looked into the concept of butterfly diagrams, and we have seen that you have a signal A and B out here. Then if it is an DIT butterfly, this will be A plus B W and K, and this will be A minus B W and K. So when we look at this particular topic, basically we can see that I have what is written here is the concept of the butterfly diagram. So here all the values are complex values. So when we look at this part, basically an output will be resultant of AR. That means A is treated as a complex value here, which is why they have the real part and the imaginary component. Similarly, B also has got its own real and imaginary component, and W and K is actually cos x minus J sin x, which we already know. So multiplying all those kind of things, you can see that the ultimate result will be AR plus BR WR plus BA WC. Now this will be the constant part of the final output, and this will be the imaginary part, not the constant but the real part of the final output, and this will be the imaginary components that make up the imaginary part of this particular final value. So just as you look over here, WR will be equal to cos x and WI will be equal to sin x. So all you need to do is multiply and open the brackets. You can see that you're combining the terms with J component, and you're combining the terms without the J component, which will result in the real part and the imaginary part that is given over here. Similarly, for B dash also you can find out a set of real component and an imaginary component. So you can see that out over here, when we calculate this particular thing, basically you can see that there are products that are involved. So basically if you look over here, you have a term called BRWR. That term also exists over here. So BAWI is also available here. BAWR is also resultant over here, and BRWI is also a part of the final output. So we have these terms BR, WR, BI, WI are represented if they are represented by 16-bit numbers. Their products are represented by the previous equation will require 32 bits as the output, and we have to truncate or round it. So basically the point mentioned here is that you have to multiply, these many multiplications are involved out here: BRWR, BIWC, BAWR and BRWI, not C, it is I. So these many 4 multiplication takes place over here with these individual components, and which will result in the rounding of errors. So there will be 4 round of errors for such butterfly, for computing one butterfly involved in the computation of these 4 components. And here basically, as you can see over here, the variance at the noise power will be the output will be 4 into q square by 12. Usually it is q square by 12, but since there are 4 multiplications that are involved, it will be resultant as 4 into q square by 12. So that will be equal to 4 into 2 raised to minus b minus 1 by 12. So that will be equal to 2 raised to minus b minus 1 whole divided by 3. And what is just mentioned here is related to computation of one butterfly, and similarly one butterfly diagram. For each butterfly you have this much error that is generated. So just imagine what will be the kind of noise that will be involved in computation of an 8-point DFT. So when we look at the 8-point DFT concept, you can see that this is the error involved with respect to one butterfly, and if you look at the 8-point diagram that we have implemented, it basically involves for computation of one value, that means you have x1, if you have the values x of 0, x of 1 up to x of 7 out over here, for computation of one value you require 7 butterflies. If you look over here, this will be the resultant of this butterfly that is carried out over here. But for this butterfly to be computed, you need these 2 butterflies to be done. So that makes it 3, and if you have to get these 2 butterflies, you need to solve these 4 butterflies. So eventually for computation of one value, that is x0 or x1 as mentioned over here, x of 0 I made it for understanding, for computation of one value, it depends on 7 butterflies, so that will be equal to n minus 1. So the total output noise variance at one output will be equal to sigma e square, that is into n minus 1 sigma b square. So that is what we have already computed out here. So that will be n minus 1 into 2 raised to minus b minus 1 whole divided by 3. Now if large values of n are being used, that means if it is not 8 point but rather 1024 or the higher values above that, maybe this n and n minus 1 wouldn't make much difference. So for larger values of n, you can consider n equivalent to n minus 1. So that would be the end of the topic for this particular section, and please follow all the videos that have been created, and do study with the material that is also provided so that you have a better understanding. Thank you.